Well done for completing the first 4 sections. You're nearly halfway through the course now, and I hope you're finding it engaging. In this section, we will show you how alternating current works. It's an important section as we will use alternating current in the power networks that we'll be studying in later courses. The aims of the course are to show the principles behind alternating current, or AC, to show the relationship between single-phase and three-phase systems, and introduce the basic AC equations. Let's now look at a typical alternating current, or AC, circuit. This time we will be using an AC generator. An AC generator starts with a coil. Let's connect 2 terminals to the coil. I'll label one live and the other one neutral. Let's send a magnet inside the coil. Firstly, the magnet is spun around inside the coil. The magnet induces a voltage in the coil wrapped around it. As soon as that happens, a voltage will appear at the terminals. To use the electricity, we need to add some conductors and a load. As soon as we have a circuit, current will flow. It flows from the live through the load and back through the neutral. Let's see what the shape of the waveform is as it comes out of the coil. Here we have an AC generator from before, and we have a positive and negative amplitude time graph for the voltage. Let's spin the magnet. Follow the red dot. Pretty obvious that over time, the voltage goes positive, and then negative, and then back to positive again, in one long cycle. Let's join the dots together. What we see is a sine wave, and the voltage alternates from positive to negative in a repeating cycle. Whenever you look in an AC system, you will always see a sine wave. To maximize the energy from the magnet, we can have 3 separate coils, spaced equally 120 degrees around the outside. So here we have a magnet from before. Let's place the first coil at the top with its own live and neutral. The second coil 120 degrees apart with its own live and neutral. And the third coil 120 degrees apart from both of those. To distinguish between the 3 coils, we call them red, yellow and blue phases. So the first coil, we'll call it red. It's got a red phase voltage and a red phase current. The second coil we'll call yellow. It's got a yellow phase voltage and a yellow phase current. And finally blue, and that's got a blue phase voltage and a blue phase current. As the coils are physically 120 degrees apart, the voltages are 120 degrees apart as well. This can be shown on a phasor diagram. First, let's put the red phase vector. Let's make it vertical as a reference point. Next is the yellow phase vector. This is 120 degrees apart from the red phase, because the coils are 120 degrees apart. Next is the blue phase vector. We connect all of the coil neutrals together at one point, called the neutral point. This ties the 3 phase voltages together into one 3-phase system. Let's look at the standard amplitude time graph. First we have the red phase sine wave. Then, 120 degrees apart, we have the yellow phase sine wave. And finally, the blue phase sine wave. Let's now draw a line from one phase to the next. in this case from the red phase to the blue phase voltages. We call this vector the phase-to-phase voltage. This line is longer than the other lines, therefore the phase-to-phase or line voltage must be higher than the phase-to-neutral voltages. In fact, by using geometry, we can work out that the line voltage is always 1.73 times longer than the phase-to-neutral voltages. Let's now look at the relationship between the phase-to-phase or line voltages and the phase-to-neutral voltages. As we said previously, line voltage VL is 1.73 times by the phase voltage V phase. The phase voltages are red to neutral, yellow to neutral, and finally blue to neutral. The line voltages are red to yellow, red to blue, and finally yellow to blue. Let's now look at the relationship between the phase-to-phase or line currents and the phase currents. Line current, IL, equals 1.73 times by the phase current, I phase. The phase currents are red, yellow, and blue. The line currents are red to yellow, red to blue, and yellow to blue. Let's now look at the three-phase power equation. Three-phase power is V line times by I line times by the power factor. It can be difficult to measure the line current, so we tend to see this version instead. Three-phase power is 1.73 times by V line times by I phase times by the power factor. The 1.73 is there as we are now using phase current instead of line current. Let's do a worked example. For a three-phase system that has a phase current of 160 amps, a phase voltage of 240 volts, and a power factor of 0.8, calculate the three-phase power drawn from the system. From the previous slide, three-phase power equals 1.73 times by the line voltage times by the phase current times by the power factor. We need line voltage for three-phase power. Therefore, the line voltage equals 1.73 times by the phase voltage. Therefore, line voltage is 1.73 times by the 240 volts from above equals 415 volts. Therefore, the three-phase power is 1.73 times by the line voltage times by the phase current times by the power factor. Let's put the numbers in now. Equals 1.73 times by 415 volts times by 160 amps times by 0.8. Therefore, the three-phase power is 91,897 watts, or 91.897 kilowatts. The frequency of an AC system is the number of sine wave cycles that occur every minute. Let's look at our previous single-phase system. Here we have a magnet inside a coil as before. As before, a sine wave is created when the magnet is spun around inside the coil. Let's now slow down the spin of the magnet. As we can see, the sine wave starts to spread out. As the speed of the magnet decreases, the frequency decreases as well. Let's now speed up the spin of the magnet again. As we can see, the sine wave is shrinking again. As the speed of the magnet increases, the frequency increases as well. The frequency is measured in hertz, where 1 hertz equals 1 sine wave or 1 cycle per second. Here's 1 cycle. 1 cycle of a sine wave is when it goes from positive to negative. In the United Kingdom, we have an AC supply with a 50 Hz system. In the United States, a 60 Hz system is used. It is impossible to connect two AC systems together unless their frequencies are the same. Let's summarize what we've learned today. In an AC system, a sine wave can be seen on both the current and voltage waveforms. We can create a three-phase system which has red, yellow and blue phases and its own unique set of equations. The frequency of an AC system is measured in hertz and is related to the speed of the magnet, i.e. the speed of the generator. Congratulations for making it halfway through the course. Understanding alternating current can be a difficult concept, so well done for getting through it. I have attached some test questions in the course content. Please try them before going on to the next section, which will introduce resistors. These are the first of the 3 types of loads we will use.